Mass defect is a really crazy thing in nuclear chemistry. And the reason it's crazy is all that talk you might heard a long time ago about being able to convert mass into energy and energy into mass. That is exactly what happens. It is so cool, but also just crazy too. So here's what happens. Here's how we explain it, at least in radiochemistry, nuclear chemistry, is we know the mass of a proton, a neutron, and an electron. Note that these numbers actually go way further than this. You can get them out a lot farther if you want to Google it and play around with that. But the AMU is a mass term, and it's kind of like gram, except that it's on such a teeny tiny scale. We lose context when we're talking about something that's like on 10 to the negative 27th. You know what I mean? So we have this AMU term, and that's how we discuss masses of tiny things. That's the unit for it. You saw it way back in General Chemistry 1 at the beginning. So we're using this term again, and what we do is we'll take something like helium. So again, note that we're taking neutral helium, which is not the same thing as an alpha particle, because an alpha particle is charged. So we're taking neutral helium. It's got 2 protons. That's what helps identify it as being helium. It's got 2 neutrons, and then it's got 2 electrons. So basically what that is 4, 2 helium. And then we say, okay, so here's the expected mass, and we just do exactly what you would think we do. We just multiply, the mass of a proton, and we've got the mass of a neutron, and then same for the mass of the electron. So we just put all those numbers in the calculator, and then this is what we get. I have my calculator going on. 2 times 1.0073 plus 2 times 1.0087 plus 2 times 0.00055. I put that in, and I get that the value is 4.033 AMUs. Look what happens when you actually experimentally determine it, though. You get this number. So there is a difference between the mass of all those particles together and the experimental mass. That difference is called the mass defect. And what it basically has done is it has taken the lost mass, that difference, it converts it to the energy needed to bind the particles together. Is that not crazy? The whole idea of being able to convert these tiny little particles into just a little bit of energy, and not even the entire particle, just some of it. And that's what's helping to bind all the particles together. So you can do all of these calculations for yourself, and the math is usually easy enough. You don't even have to see, I'm doing it by hand even. You don't even have to get out a calculator if you don't want to. So that's how much mass is converted into energy. And there are other equations that you can then use to convert that into actual energy, to have it in terms of joules, or more commonly MeVs, which is electron volts. You can do conversions like that, but we won't actually do that. We're just going to ask you how much mass is involved. So to work these kinds of problems, all you need to know is that you've got this table available. You can keep those numbers like that. And you can do all your own calculations, because once you know what the atom is and you know the mass number, you've got these. And if you know that it's neutral, then it's going to have the same number of protons and electrons if it's neutral. You just do the multiplying, you get a number, and then we will have to provide you with the experimental mass number. Or you can go and look at the periodic chart, and you can just be like, oh, wait, what is that on a periodic chart? See, it's so small, though, our periodic charts only go to the hundredths place. If you find a periodic chart online, you likely will be able to find the experimental number. But that's actually where we store it, is on some big old fancy periodic charts with lots and lots of numbers. So there you go. Easy peasy.